Hi everyone. Today we're going to be talking about context behaviors as it relates to enemy AI in your game projects. So what are context behaviors? Essentially, they're things that enable your agents to merge multiple decision trees from the world as it appears to them in that given time frame. So this is in contrast to steering behaviors, which are typically single tree decisions. But how do they do that? So the way they do it is they basically use a context map, which is basically, you can think of it like an array of possible directions that they can actually travel. So your context maps can vary in size and what we call resolutions, basically. So what decisions do we merge to actually define those directions? So in order to define a direction, you need to define an array of interests and an array of dangers. Then you basically populate float values into both of those based on your project's needs. As an example, an interest might be a player's location. A danger might be an obstacle, like a fence or a wall or a rock. Basically, once you have those interests and those dangers, you then want to remove the interests that overlap the dangers. There's a few ways you can do that. You can, of course, just subtract them, or you can simply run like a for loop and then check if there is a danger in place of an interest, and then if there is, you can simply set that interest to 0 or set it to some negative value if you want to weight it. But once you've done that, you then basically multiply the remaining interests against the entirety of your context maps, and that will basically define your chosen direction. But how do we actually define float values for your interests? Well, let's go ahead and jump into some of the code here. Just real quick, I'll do a brief overview. I have some variables. I define, a max speed. I defined a steering force, which just helps with some of the, the jitteriness, but more on that a little bit later. And then I defined a look ahead scalar value. That's basically, we're going to be doing some ray casting, so that's going to be the length of my ray cast, basically. And then I defined a resolution, and that's going to be it's going to be for the entirety of the system. So it's basically how much data or how much information is going to contextually go into your AI so it can make a more informed decision. And then, of course, I have a target. In this target, you can see it in the inspector on the right. I have defined it to be the player. So you can make your enemies chase any particular targets. In this prototype, we're going to use the player, and just make it that simple. And then I defined 3 empty arrays. These arrays, of course, are called my context map, which is effectively, the possible directions, and then an interest array, and then a dangers array, and they're all empty currently. And then the last variable I've defined is just this chosen direction, and I set it to a vector of 0, 0. So pretty straightforward, but we're looking in how we define float values for our interests. So I have a function called setInterests. So in this function, I am basically defining a new variable called direction. I am then taking my target's global position and I am subtracting my AI or my agent's global position. Once I have that defined, I then take the normalized vector from that, and then I iterate against my direction map or my context map. And then I basically say my interests are going to be equal to the dot product between that direction and the direction in my context map. So basically, the way we define these float values for the interests is by using vector math and the dot product. The dot product has some interesting results. You typically want to work with normalized vectors, and if you are working with normalized vectors, you will get when you multiply the dot product between 2 direction vectors, you will get either -1, some value between -1 and 1. If you get -1, your direction vectors are going to be facing opposite one another. If you get a value closer to 1 or 1, they're going to be in parallel, so basically lined up. The reason that's useful is because in this particular instance, we are telling our agent to find a particular direction that is closely aligned with the the product of the direction, which is our global position, subtracted from our target's global position. So we're basically trying to find a direction that is very similar to the direction that our target is in. So basically we're looking for a value close to 1, and if we can't find that, we find the highest value among our array. And then the last thing about dot products is if you get a value close to 0 or equal to 0, your direction vectors are typically perpendicular. So that can be useful in all sorts of different scenarios. So you'll probably find that you'll be using dot product a lot in game development. So it's a good subject to cover. But this is my code on how I basically get those interest values. So I'm basically just getting the dot product between the target's position's direction and the direction in my context map. And then that's going to spit out a number between -1 and 1. And we basically are going to be looking for directions that gave us a value of close to 1 or the highest, because that'll mean it'll be in a direction closely pointing towards a target, basically. So that defines our interest. How do we define the float values for our dangers? Well, basically we just use raycasts in the world and then just go off the collisions. So I have a function called setDangers. And if you're familiar with raycasting in Godot, this is going to be right out of the textbook, so a lot of this is going to look familiar. We basically define a variable called spaceState, and we set it equal to getWorld2D, and then we call the directSpaceState method here. So once we have that, we then iterate across the resolution of our system. So in this case, we're using 8, so iterate 8 times. We're going to define a query variable and set it equal to a raycast create, and set the position to the current position, and then the end position is going to be the current position plus the direction of our context maps times our scalar value of look ahead, which in this case I was using 50. You can think of this value as basically how long you want that direction vector to shoot out. From the actual raycast, basically how long you want the raycast to be. We then define a variable called result, and we set it equal to the intersect ray between the space state against the query result here. So basically it's going to check each of the raycasts and see if it hits something. If it hits something, it'll populate it with info. If it doesn't, it's going to be null or empty. So we can then iterate across our danger array, and then we can set the dangers element to either 1 if the result has something, or 0 if it doesn't have anything. And this is just very basic. You can of course tailor your particular needs however you want it, but basically if this raycast hits anything, it sets it to 1, so basically the agent will then basically add that to its danger maps. So we now have our interests and our dangers defined. How do we choose a direction? Well, the way you do that is you basically have to merge your interests and your dangers decision trees. Once you've done that, you then multiply your context map or your direction map against your interest map. And then you add up all those values together until you have one final direction vector. And then you normalize that vector. So let's take a look at that. So we got this function called choseDirection. We are, of course, setting chosen direction to vector2.0. We did that at the top here, but we are iterating across this, so this is just a safety sanity check. And then iterating, we're going to say for the based on the resolution of our map, so how many elements, which in this case is 8. So we're going to iterate 8 times, and we're going to say if the elements in the danger array are greater than 0. Basically if they're 0 or 1, right? If they're greater than 0, that means our raycast hit something. So we're then going to set that overlapping interest element, because it shares the elements here. And in this case, I'm setting it to -3 because I'm weighting it. So I want want my agent to really avoid this. Because it hit something, I want him to go the other direction or go away. You can, of course, just set this to 0. Either way is fine. You'll get different behaviors depending on, whether you're using weighting or not. So it's completely optional. Once I've done that, I then set the chosen direction to be equal to the chosen direction plus the result of the context map, which is our map of directions, multiplied against our map of interests. The reason this works is you can think of, in this case, it's an array of 8 elements, and then each of the elements, the interests are multiplying against the context, so basically the directions. So we have 8 possible directions in this example. Once you multiply it against them on the interest, some values are going to be higher than others. So some values are going to be, negative. Other values are going to be close to 0, and then other values are going to be close to 1. So because of that, you can basically add them all together, and some are going to negate each other out. So typically with this, you want some emergent behavior to come out, and that's going to happen because you're combining all the directions. And if you get 0, the agent doesn't want to move or go anywhere because he doesn't know what's going on. So there's either there's too many dangers around them, or there's not enough interests in other directions, so they kind of freeze up. But there's likely going to be one direction that is going to be close to 1 or higher than 0. So the agent is going to want to move towards that direction. You'll get some sort of emergent behavior when you basically merge this decision tree. And then once we've done that, we will then take that chosen direction and normalize it. It just makes life a little bit easier because you're going to be multiplying this probably based on a scalar. When you're moving, you probably find that you're multiplying against some speed or something. So it's easy to work with normalized vectors when you do that to get consistent movement, I guess. But yeah, so that's how we choose our direction. So we have our interests, we have our dangers, we've chosen our direction. But how do we define our directions or our context maps? Well, the easiest way is you just take a circle and you divide that against your resolution. So we're going to take a look at the ready function here. In the ready function, we're doing a few things. We are resizing our arrays, our interest, dangers, and our context maps based on the resolution, which in this case was 8. We're then iterating across that resolution, and we're defining an angle, and we're setting that angle equal to the element times tau. If you don't know what tau is, it's just pi times 2, or it's a circle, or 360 degrees. Pi is half a circle, or 180 degrees. So whatever, you can do it either way. You can do 2 pi or tau, or however you want to do it. So once you multiply those together, you then divide it against your resolution, or how many directions you have, basically, or how many directions you want. And this is basically going to take a circle, and it's going to cut it up, however many times you decide. And then we set the context map based on the vector 2 right, which is a vector 1, 0, just facing to the right, rotated across whatever that angle. So the first iteration will be 0 times 360, which is 0, divided by 8 is going to be 0. So this is going to take a right vector and rotate it 0 degrees. The next time it goes through, it'll do 1 times 360 divided by 8, which is going to be 45 degrees. So actually, I could probably just make this easy and do... Godot does math in radians instead of degrees. So to make this more readable, we'll take angle and set it equal to radians to degrees and pass in angle. And then we can just simply print that angle. So we're using a resolution of 8, so it should cut up our circle 8 times. And you'll notice down here, we start at 0, then 45, then 90, then 135, 180, 225, so on and so forth. And if you change your resolution, like say I go to 4, then we should only have 90, 180, 270, and then it'll go back to 0. 360 and 0 are basically the same in this context. So then you can see that right here, 90, 180, 270, and then it basically loops back because we're cutting it four times. So hopefully that makes sense. But yeah, so once we can probably get rid of this code here because we don't need it. But yeah, so then we're basically setting up our context map, which is our direction map, based on that circle cut up that many times, however you want to do it. So we've talked a lot about context resolution, but I guess we never really defined it. You probably figured it out by now. It's essentially the number of raycasts you wish to use. The more you use, the more accurate your agents will be, but this will of course be an increased overhead. So as an example, I can set a resolution of 3, and then I have 3 ray casts. The blue represents directions that the agent wants to go, and the red represents directions the agent wants to avoid. Now I can move over here, and the agent's going to do its best to move over. As it detects something, it'll move away from it. But you can notice with, it does a pretty good job. I don't think you need many ray casts for most decent movement. But it can get stuck with, like lower resolutions, right? Because it doesn't have much data. It doesn't have enough context, basically, to make an informed decision. So you may still run into situations that you probably ran into with other setups where, it gets stuck behind an object. On the flip side, if you increase the resolution to something like 32, it has a lot more data that it can actually feed into the agent, so it can make a lot more informed decisions. And you usually will get, more informed movement or better movement, so it can, basically navigate around obstacles a little easier. Still not perfect, but for what the system can do, it's pretty good. But that brings us into our next topic. What optimizations are available with this type of system? Well, if you're familiar with any other game development engines, you're probably familiar with level of detail optimization. So basically, wherever the player's looking or the camera's looking, you want to do a lot of the heavy lifting there, and have your system basically do all the work there. And then for players, or for areas of the map that are not available to the camera or further away from the player, you generally don't render as much, and basically it's looks a little terrible. But this system can basically do something similar, right? So let's go ahead and set our resolution back to, we'll do 8. I'm going to go down to my draw function, enable my optimization function here. And then before I talk over it, let me just kind of show you what it does. So based on the distance to the player, the resolution map will basically increase. So you see it's a higher resolution the closer I am. As I get further away, the resolution goes down. Now this helps because there's not as much overhead on the agent or on the system. And it makes sense because as the player's further away, the agent probably doesn't need to be super accurate, because the player's likely not going to see this because your camera's going to be zoomed in and these agents are going to be further away. So this level of detail or LOD optimization is something you can implement with this sort of setup. So just as a brief, quick overview, you can see I defined a distance variable, and I set that equal to be the target's global position minus the entity or the agent's global position. And then I take that distance value and I get the absolute value of it because I don't want to deal with any negatives. And then I can just take the X value from that distance, and I can say if it's less than 200 pixels, I will adjust my resolution to be 16. If it's greater than 200 but less than 400, I will set the resolution to be 8. And then if it's greater than 400, so basically it's really far away, I can dumb down the resolution to 4. That way it's less work that the system has to do. From there, I basically resize my arrays based on that new resolution value. I then iterate based on that resolution, and I do the same code that we did in the ready function, which is basically I'm defining an angle. I'm setting that angle equal to a circle, and then I'm dividing that circle based on the resolution, so how many cuts I want to make. And then I iterate across the context map, which is an array of our directions, and then I set the right vector to be rotated based on that angle. Very simple. And then I guess the only other things I didn't show is, of course, this draw function. You can probably disregard this. This is just jank code that made that little pie thing that you see when I'm moving around. Nothing too crazy there. And then the only other thing I didn't go over was the physics process function. So there's not too much here either. I'm basically I'm setting the interests. I'm then setting the dangers. I'm then telling it to choose a direction. This is for that little widget, the that you saw on the left-hand corner, so you can ignore that. That's a Godot function. And then I'm just setting the velocity to linear interpolate between my chosen direction times my max speed, and then I'm smoothing that out across that steer force that I called out that I made earlier. And that's just to prevent a little bit of jittering, but this system actually works pretty well, and I don't think this is really needed. And then I'm calling, of course, move and slide to actually do the movement based on this velocity. So, yeah, I think that's pretty much it. I think the system works pretty good. But yeah, I hope you enjoyed this explanation of context behaviors, but as always, thanks for watching, and see you on the next one.